Hello everyone, this is Marnali and for today's video we're going to talk about interpolation. Now what is actually interpolation? For that we need to define a function that is y is equals to fx, where x is said to be between x0 and xn. For every value of x there has to be a value of y which can have more than one value. Now if the function is single valued and continuous and is known explicitly, then the value of fx corresponding to a certain given x, says x0, x1, xn, is can be computed easily and tabulated easily. Converse to this situation, we have some set of tabulated values, that is x0, y0, x1, y1, x2, y2, which actually satisfy the relation of y is equals to fx. Now the thing is, we do not know the explicit value of fx here. To find that function, we need to find another function, that is psi x. Now this psi x can be formulated from all the tabulated values that we are supposed to take out from all the methods that we're gonna learn in next couple of videos, which are finite differences. Now the whole situation that I have right now explained is actually known as interpolation. Now the fx and psi x should agree on the set of tabulated values points to give a value of interpolation. This psi x is a polynomial, and the process that is been done on it is actually polynomial interpolation, and psi x is the interpolating polynomial. There are different types of interpolation. For now, we only have to be concerned about polynomial interpolation. The study of interpolation is based actually on the concept of finite differences, which actually talks about the changes that takes place when we generate a value for every function, and which is said to be finite. The changes that are being made are finite, and it is in the independent variables. And for the what is actually finite differences? For that we have to take a function, that is y is equals to fx. There is said to be some equally spaced set of values for x. We have to take x, and we have some equally spaced values of x that has to be computed with xi is equals to x0 plus I h. And now what is h? H is the difference equal space between x0 to x1, x2, which goes on till xn. I is the values that we need to find, the terms that we need to find. We also have also have a table of values for xi and yi, where again I is the terms till 0 to n. Now to find the value of fx, we need to have some intermediate values of x. There has to be some difference value of x, or the derivative of fx for some x in the range of x0 to xn. Now this is the basic concept of finite differences. There are three major types of finite differences, that is forward differences, backward differences, and center differences. Now today we will talk about only forward differences. For the next video we will talk about backward differences. Now what is forward differences? For that we have to have some set of values of y as in which denotes y0, y1, y2 till yn. This is some sort of a set of value of x. And now we have now for the fx already said, for finite differences we need some intermediate values or the derivative of it. For now here we need to have some differences of of y. I'm sorry. Then for that differences, you may know, we also already know that we need to subtract the next term to the first term. I mean the next term to the previous term. We have to subtract both of them. The differences of y is denoted by delta, and the triangle shaped is actually delta. Delta y naught, delta y1, which goes up to delta yn minus 1 respectively. And what is this difference of y? I mean the first degree of this differences is known as first forward differences, where we see that the delta is the first degree, I mean the first degree of difference. Now where we are seeing that delta y0 is equals to y1 minus y0. You can see that, which is actually what is that, y1 is equals to y0. And where we would find this y, the value of y, we would get from that function that we have taken earlier, which is y is equals to fx. For you have to keep the x value, x1 value, to get the y value for the corresponding value of y1. For this we from this we could say we have found the first forward differences, which is delta y0 is equals to y1 minus y0, the next term minus the previous term. We have to do it till a generalized form that we have got is delta yn minus 1 is equals to yn minus 1. The delta here is known as forward difference operator. The differences of the first forward differences are called second. And now to get the second degree of first of forward differences, we need to subtract the differences of the first forward differences. We have taken out delta y0, we have taken out delta y1. To get the second degree, I mean the delta square y0, we need to subtract delta y1 minus delta y0. In this process we would get the second forward difference. It is the second forward differences, as you can see, is denoted by delta square y0, delta square y1. Similarly, one can define third difference formula, fourth difference formula in the same way. We could say that all the forward differences are derived from the first forward difference that we have generated from delta y0. Delta y0, delta yn, this would actually this would be the difference for second forward difference. This would be the second forward difference would be the difference for third forward difference, and that is that's how we are supposed to move forward. And this is how, and that's why the name of the finite differences forward differences, as we are moving in a positive we are moving forward. As you can see, the whole process of second degree the second forward differences, that is delta y1 minus delta y0 here, where we can say y2 minus y1 minus y1 minus y2 is equals to y2 minus 2y1 plus y0. We would get a generalized form of all the forward differences. In the in general we could say delta p by r is equals to p minus 1 y r plus 1 minus, as you can see, the whole formula written here. Therefore, we can say that the higher order differences can easily be expressed in terms of ordinates. Uh, uh, since the coefficient occurring on the right side are binomial coefficients. And this differences that we have taken is all known as forward differences. The forward differences is actually being used in next couple of videos that we would say for the Newton Gregory forward difference that we would use, and we have another formula for that, that's a part of this is just the forward difference method. We also have an interpolation difference difference formula. For that we use forward difference. Forward difference table, you can see we create x, y, delta, delta z, delta square, delta cube, delta to the power 4, delta to the power 5, delta to the power 6, where we uh, where we formulate the whole table through a long process. I mean, the way we y1 minus y2 we would get delta y0, for y2 minus y1 we would get delta y1, for y3 minus y2 we would get delta y2, for y4 minus y3 we would get delta y3. This is how we would get the whole forward difference table. And for now we had seen the whole forward difference. To summarize the whole thing, we actually started with the finite differences, where we took a function set in for a value of x, and x equation which was xi is equals to x0 plus ih, and where we took an equally spaced set of values. We said to have some derivative values of x to get the differences of the function. We introduced the first type of difference, which was forward difference, where uh, uh, we had set of values of y, which was y0, y1, y0, y2, yn, which then which then was used to create the first forward differences. The first forward differences were used to create the second, and so on. Through this, we had a generalized formula of that you can see here in general that we have used, and this whole formula was to generate R for forward differences. This different and these differences forward differences values were set and formulated in a table which is known as forward differences table, where we have um, kept the taken the numbers, I mean the variables x naught and y naught, and we have generated all the values of um, first forward difference, second forward difference, and so on. With this, the forward difference table is over. Thank you for this video. Um, for the differences that we are taking out is same as the differences that we generated in forward differences. Why do we need this differences? We need to find the intermediate values of x to find the value of our function. The differences here is same as the forward difference method. The uh, the only difference here is the operator, which is nabla. Nabla, as you can see, there is a triangle, a downward triangular shape, which is called nabla. It is also called backward difference operator. The nabla is actually just the opposite of our delta. And to generate the first backward differences, we need to find the value of nabla y1, which we would get from y1 minus y2 or y0. We will to generate the value of nabla y2, we have to take out the value of y2 minus y1. This would actually get us our first backward difference. As you can see that the process here is same as the process that we did in uh, second backward, as in first forward differences. The whole process is same. The only thing different is the operator. As I already said, the operator is the only difference. The next procedure would be followed as same as the forward difference. I mean, we need to have our uh, first backward differences, as in the nabla y1, nabla y2, to get the second backward differences, which is nabla square y2, nabla square y3, so that we could generate the value of second backward difference and the third backward difference. Through these methods of backward differences, we could uh, we could generate the whole backward difference table, just as same as the forward difference table. The only thing I already told you, the only thing that we change is the forward or the operator. You may ask, okay, why do we need the backward difference table when we already have the forward difference table? For When we talk about the forward difference table, we usually take the values which are in the in the first couple of I mean the first couple of in the range as same as the first couple of data points. And for backward differences, we have to take the data points from the bottom. I mean, we have to go from the bottom. For forward difference table, we have to go top down. And for the backward differences, for we need to go from bottom to top. And that's how we are supposed to generate the backward difference table. I mean, that's like why this is how it would generate the value of nabla y1, nabla y2, nabla y3, and that as you can see here, y1 minus y0 would give the value of nabla y1, where y2 minus y1 would give the value of y2, nabla y2. The y3 minus y2 would give the value of nabla y3, and so on. We would get the whole the whole table of backward difference. And that ends with the backward differences. We have already covered the forward. This was the backward differences. To summarize this is actually just the difference about the difference between forward and backward differences is that we use a different type of operator. That when we talk about backward difference, we talk from the bottom to the, I mean, we need to find the data points after we need to find the points lying out after the data points, and either that or either the ones which are at the end of the range of x x xn. I mean the last data points. And for the And for the forward differences, we need to find the first few data points. Either we have to uh, find the data above above the data points, or either the first couple of data points. For that, we need forward difference, and for the last couple of data points, we need backward. It can be used to find the data points outside. I mean, after the before the date. I mean, before the data points. The shift operator. It is defined as the operation that increases the argument x by h. I mean, the x that we have taken for the function function y is equals to fx. And for forward difference, there was this h that was always added when we were taking out any value of forward difference. And what was this h? H was the equal space between all the set of values. Now the shift operator is multiplied to the fx value. And the and the value of h would increase with respect to our shift operator. The Here we can see that in increasing the degree of 3, I mean the degree of the shift operator, the value of h is increased by the same degree. I mean the value of h would change with the same number as the degree. Here we can see in an example, we can see e to the power, when is to the power 1, we could see the h is only one time. When the e increases to the power 2, the h also is doubled. When the e is to the power 3, the h is also tripled. In the same manner, when we inverse the operator, e to the power minus 1, the minus 1 here that we have taken as a real number is also placed in front of the h. And so minus 1 plus h would give us the answer as fx minus h. This would give an if we change the fx value by yx, it was at the end of the day, the whole function was y is equals to fx. And so to get in the equation as y, we would replace the fx function by yx and have a generalized form here that you can see is e to the power n yx is equals to yx plus nh, where n is supposed to be any sort of real number. This was shift operator. Now with the help of shift operator, we would also know the relationship between central difference operator. Now, what is central difference? It is a type of finite difference that we have talked about in previous videos. Now, central difference is when here we can see that there are 2 points, which is x plus h by 2, x minus h by 2, and the difference between both the points is measured by h. And so we place the value x minus h by 2 and the f in the f equation, and the x plus h by 2 here in the equation. We could see that the next term is subtracted from the previous term. Where does this doesn't this sound similar? It was the same thing as forward difference. The forward difference had the same method. It it took the previous term and subtracted from the the next term was subtracted by the subtracted from the previous term. And the only difference here is the h that we have taken in forward difference is halved. the value of h that we have taken here is half. And so the central difference operator, now the operator that we are using here is delta fx. What is delta fx? Delta fx is the delta is actually the central difference operator that we're going to use in the in the central difference. Just like we had delta for forward difference, we had nepla for backward difference, we have this delta for central difference. Now we put the value of delta fx is equals to fx plus h by 2 minus fx minus h by 2. As you can see, this is a formula derived from forward differences, and so we can write it in this manner: delta fx is equals to delta fx minus 1. Both the deltas are different. One represent the triangle symbol represent the forward difference, and this sign this symbol reference the central difference. Both of them are different, and we have to take out any relationship between both the operators. Now delta fx is equals to the delta forward difference shift operator to the power minus 1 by 2 fx. How can we say this? Because x plus h by 2, fx plus x by 2 is actually our e to the power 1 minus 1 by 2. We have already seen here that the e to the power n is equals to yx is equals to yx plus h, and as we have used this form here itself, here also. And so we had the whole operator, which was we replaced the whole delta fx minus h by 2 with the shift operator e to the power minus 1 by 2 fx. This was the whole thing. We just used the shift operator formula that we have seen in the earlier point. Now we could say the delta is congruent to the delta e to the power minus half. E to the power minus half. This is the relationship between the central difference is the forward difference and the shift operator. With this, we also have an averaging operator. You can have a look throughout the video. I have already you can see that it is similar to the things that we have did here. Like we have fx plus h by 2 plus fx minus by 2. This is the mu fx. Mu fx is our averaging operator, which was divided by 2. So we just replacing the values to get any sort of relationship between all the operators that we are using. With this, the central difference and the finite differences ends, and we have examples here. We could see there is a mu relationship between the central difference and both of them have any sort of relationship. In this way, all the operators can have a relationship between any other operator. So thank you for this video.